4.2, uniform distributions. So uniform distribution occurs when, in a single trial, all outcomes are equally likely. So the probability of a discrete uniform distribution, all outcomes have the same probability of being observed. We just do 1 over n being the total number of possible outcomes in that experiment. And for the expected value for discrete probability distribution, okay, the expected outcome for an event is just the outcome times its probability. The next outcome times its probability, okay, all the way down for every single outcome and every single probability. So let's take a look at rolling a 6-sided die. So determine the probability of outcomes when rolling a single 6-sided die, then graph the distribution. So if you think about the outcomes on a 6-sided die, they're 1, 2, 3, 4, 5, and 6. And the probability of all of them are equal. They're all 1 over 6. Okay, so when we draw the bar graph or the distribution, 1 divided by 6 is let's say 17. Yeah, let's just round to 0.17. So 1, 2, 3, 4, 5, 6. And if you notice that the scale on the y-axis is 0 to 1, it's because the probability can be between 0 and 1, including both. Now, determine the probability distribution of the outcomes when spinning a spinner with 5 equal sections. So instead of the outcomes being 1 to 6, now they're just 1, 2, 3, 4, and 5. And the probability of each occurring is 1/5, which is 0.2. So the probability of 1 occurring is 0.2. Oh, I was doing 0.5. 0.2, 2, 3, 4, and 5. There's no 6, so we stop there. And I want to point out the most important trend on these two bar graphs here. All of these bars have the same height. They have equal probability. That's what makes them uniform. Okay, so that makes it uniform. Okay, and as a reminder, the bars don't touch because it is discrete. Then we're going to take a look at what a fair game is. Okay, this occurs when the expected value is 0. That is the definition. So as n approaches infinity, each player has an equal outcome or like payout. Okay, it's not always the equal probability of winning. It depends on the payout. Okay, the probability may be the same, but if the payout might be different. It depends on the money payout or the allocation of points. Okay, so example 3. Consider a game where you roll a 6-sided die. Okay, so let's stop there for a second. We can roll a 1, 2, 3, 4, 5, or 6. Okay, but here's the point allocation. If the result is an even number, you earn equal to twice the value of that roll. So we have these 3 as equal number or even numbers. So our payout would be plus $4, plus $8, and plus $12 because it'd be double that. And now if it's an odd number, which is 1, 3, and 5, we're going to lose 3 times the value of that roll. So if we roll a 1, we lose $3. If we roll a 3, we lose $9. And if we roll a 5, we lose $15. Okay, when we say lose, we need to put that negative sign on the number, on the payout, because we're going into the negatives. And now if we talk about rolling a die, the probability is still 1 over 6 the entire way down. That's a uniform distribution. And that's going to add to 6 over 6, which is 1. So what we've done is we've taken into account every single outcome there. Okay, so we've shown the probability distribution of points in the game. And now let's actually calculate the expected value. Let's go to blue. So this chart actually tells us what to do. It's saying multiply x times p at x. So this would be negative 3 over 6. This one would be 4 over 6, negative 9 over 6, 8 over 6, negative 15 over 6, and this one would be 12 over 6. Okay, I tend to not reduce any of these because I want to just simply add or subtract the numerators. Because we know that with the common denominator 6, we can just work with the numerators. So I get negative 3 over 6, which is negative 0.50, okay? Or negative 0.5. We don't actually need the extra 0 there because it's not money, okay? So what does the expected value of negative 0.5 actually mean? So the expected value of negative 0.5 means as this person plays, as the game is played, essentially more and more times, right? Because we're trying to quote this as n approaches infinity, but in the context of the question, as the game is played more and more times, the player will lose 0.5 points for each game played. Game played. Okay. Is this a fair game? So, no, this is not a fair game. Because the expected value does not equal 0. Okay, so this is actually in favor of, like, we call it the house. It's in favor of the house. So I'll put that in brackets, in favor of the house. And all that means is that whoever's like dealing, like the dealer, that's the house. So I want to highlight this. Technically, same probability of rolling an odd and an even. However, because the point allocation is different, we can't base our explanation of it not being a fair game on the probabilities not being the same, because that's incorrect. Is the payout, okay, that you want to focus on. Okay, spinner game. Consider a game at the casino where you spin the spinner on the right with all equal sections. If the spinner lands on an even number, you win 3 times that number in dollars. Okay, so now we're talking about money. Let's take a look at the spinner. We could potentially roll a 1, 2, 3, or 5. Now, even numbers, which are, it's only the 2, it pays out 3 times. So the payout is going to be $6. Now, if it lands on an odd number, you lose double. You lose twice that number in dollars. So for 1, you would lose $2. If you roll a 3, you lose $6. And if you roll a 5, you lose $10. Okay? So the probability of rolling a 1 is 3 out of 8. Probability of rolling a 2 is 2 out of 8. Probability of rolling a 3 is 2 out of 8. Probability of rolling a 5 is 1 out of 8. Okay, so this does add up to 1. This is a complete probability distribution. We've taken into account all of the probabilities. And now what we want to do, and I'll do it in blue again, is we want to multiply the actual payout in dollars by the probability. Okay, again, leave the denominator, do not reduce, because when we get down to the expected value, we can just add or subtract the numerators. So negative 2 times 3 is negative 6. 6 times 2 is 12. Negative 6 times 2 is negative 12. Negative 10 times 1 is negative 10. Okay, so I get negative 16 over 8, which is negative 2.00. Okay, I put this in because we're talking about money, and money in Canada goes to 2 decimals. So we've shown the probability distribution of money won in the game. We calculated the expected value. Now let's interpret, what does this mean? So the expected value of negative $2 means, as this game is played more and more, we can expect let's say to lose $2 each time. Okay? So, but that's over a long period of time. So yes, you may win this $6 a bunch of times, but over the longer period of time as n approaches infinity, because the n approaches infinity in this case means number of games played. As the number of games played approaches infinity. That's what that means this time. Okay, you're going to lose $2 per game. Now, is this a fair game? So, no, it's not a fair game. Because the expected value does not equal 0. This is the straight definition. Okay? And we can also say the game is in favor of the house, because the player is not the one winning. The house would be winning that $2. Okay. Why may the owner of a casino wish to not have fair games in his or her casino? Okay. So let's just say casino owners want to make money. So fair games okay, they would not allow the owner to make money to, we can say, flip a profit. And then, like, since there's overhead and there's expenses, they would actually lose money. Okay?